Hello everyone. So in this video lecture we are going to discuss about various type of examples, right, which are based on competitive examinations only. Okay. Gamexene. Now first to discuss what is this compound gamexene. So dear students, gamexene was a compound which was first of all find out as an insecticidal properties, okay, which is widely used in pharmaceutical industries, in agriculture field for killing the insects, okay, which destroy the crops and all. Clear? So this compound, let me first tell you how it is prepared. General method used is reaction of benzene with Cl2. It is used 3 moles, okay, in the presence of ultraviolet light, UV light, and temperature used is high temperature, approximately 500 Kelvin, okay. Then the compound which you get is one, two, three, four, five, 6. So we are having 6 chlorine, 6 hydrogen and 6 carbon. So it is called as C6, H6, Cl6. Okay. It is also represented as 666. Clear? If I say about molecular formula, then this compound only is also called as benzene hexachloride. Now you may doubt, sir, this is not a benzene, right? So incorrectly it is called as benzene hexachloride, BHC. You have to remember this. When you say about BHC, it is about 666. Okay. Now if you observe this compound, then you can see it is not having any chiral center. Why? Because from this carbon, if I check, suppose from this carbon, chlorine, hydrogen, but this side and this side are same, right? Clear? But if we have to check the stereoisomers, then we have different possibilities for this compound. How? Because it is having 6 chlorine, that all 6 chlorine may be on same side, 1 may be different side, 2 may be different side, 3 may be different side. Now when you say 4 different side, means 2 on same side, that is same. Okay. So among these different types of stereoisomers of this BHC, one of the form is gamexene, okay, which is also called as lindane or gamelin or gamma BHC, because it is actually gamma form. That particular gamexene, the stereoisomer of BHC which is having gamma form, is particularly called as gamexene. Okay, so let's draw all the stereoisomers for BHC. See, this reaction is called as addition reaction. Okay. Here 3 moles of chlorine atoms have been added. Alkene, benzene is also an alkene, right, which acts as a nucleophile, and this is here as an electrophile. So it is addition reaction. 3 moles are added, 6 chlorine atoms. Okay. So total isomers, stereo, this is your question. Okay, first of all draw by yourself. So dear students, here I have drawn the normal case. Okay, now let me take all the cases. So first case can be taking all the chlorine atoms on same side. See, this is one of the stereoisomer where all the chlorines are on same side, means definitely all the hydrogen atoms will also be on the same side. Here we are having plane of symmetry. See, if you cut like this, means 1/4 portion, either this part or this part, in that way you are having plane of symmetry. Okay. Now I am taking one chlorine on different side. See, when I say one chlorine on different side, it may be any of the chlorine, right? Because all are identical. Also, numbering can be done here from all the sides, any part, right? You remember the formula? So here, in this one on different side means 5 on same side. This one possibility only. Here, it is having plane of symmetry when you cut including this chlorine on different side with this one, okay? So you are having POS here, not COS. Now I am taking the case of 2 chlorine on same sides, 2 chlorine. So let me draw first 1, 2 position on same side. See, when you say 1, 2 on same side, there is a possibility of 1, 3 on same side. One, 3 on same side. One more possibility. One, 4 on same side. Okay, 1, 4. So these all cases only for 2 on same side. When I say 2 on same side, by default it is 4 on different side or 4 on same side. So 1, 2, 1, 3, 1, 4. Now you cannot say 1, 5. Suppose if I say 1, 5, that is by default 1, 3 only. Okay. So 3 cases. 3 on same side. Now 3 on same side may be 1, 2, 3 on same side. Okay, 1, 2, 3 on same side. One, 2, and 4 on same side. Okay, 1, 2, 4 on same side. Now there is one more possibility. See, 1, 2, 3 is over, 1, 2, 4 is over, 1, 2 this side, that will be again. Now keeping all in 1 by 1, then 1, 3, 5. 1, 3, 5 on same side. Okay. See, now if you can think any other possibility among these, you cannot get. Why? All same side, one different side, two different side, two different side, 3 cases. 1, 2, 1, 3, 1, 4. 3 different side, 1, 2, 3, 1, 2, 4 or 1, 3. Then you cannot make adjacent to this or this. So 1, 3, 5 simply. These all cases are possible. Now when I say 4 on same side, means simply 2 on different side. This all covered already. Now these are the all possible cases which I can draw for this compound 666. Okay, this is your 666, or this is called as gamexene, then BHC, gamelin. All these names are used. Okay, in reality it is 1, 2, 3, 4, 5, 6 hexa chloro cyclohexane. Okay, so this is your IUPAC name, and these all are other names used. Now one by one, let's discuss in this compound which one is optically active, which is optically inactive. First of all, check this one. If I say this one, then you can make plane of symmetry through this. So it is inactive. Check this one. One chlorine on different side. You can make that chlorine and this one plane of symmetry. So it is inactive. Check this one. When 1,2 chlorine on same side, then taking the plane which cuts these two in equal halves, means in between this, then you can have plane of symmetry. So you can say plane of symmetry present. Okay. Now check this one, 1,3. So when 1,3 same side, then taking this part, this plane from this two portion, okay, you can say this is having plane of symmetry. So it is inactive. Now check this one, 1,4. So simply you can cut like this, okay, this part. So it will be your inactive. Now as I was telling, one of the stereoisomer is named as gamexene. That particular part or lindane, this one, okay, this one is called as lindane or gamexene. Clear? 1,4 on different side, means with respect to all other fours, okay, means position number 1 and 4, these two will be same side, remaining 2, 3 and 5, 6 will be on same side. So this one is also optically inactive. Clear? Now check this one. Here what I see is, if I take the center point, see, if you have to check the plane of symmetry, it is not possible here. Why? If I take this plane, then what I say, this part is the mirror image of this part, right? So when I select this plane, then this part cannot be the mirror image of this part, okay? So plane of symmetry is not possible here. But if I take the center part, taking the center part, I can say this is towards you, this is away from you. So making a line which covers this one and this one, yes, it is possible, center of symmetry present. Again, with respect to this also, with respect to this also, so it is also optically inactive. Okay. Now check this one, 1, 2, 4. See, here it is a problem. You cannot make any symmetrical part here. How? Plane of symmetry also not possible and center of symmetry also not possible. Okay. So it is your active part, means we need to consider its mirror image part, means its enantiomer part. What that will be? That will be simply, see, 1, 2 and 4 on same side, dash. So its mirror image will be 1, 2 and 4 on wedge, remaining on dash. Simple. Okay. Now check this one. Yes. Here simply what I can say, taking this plane, this plane, I can make it symmetrical. It is having symmetry. So it is also inactive. Okay. So dear students, in this compound you can understand it is having total 1, 2, 3, 4, 5, 6, 7, 8. 8 different stereoisomers, out of which one is active. So total will be 9. So there are 9 stereoisomers for benzene hexachloride, out of which 7 are optically inactive and 1 is active. So its mirror image is also considered. Clear? Done? Okay. So you can see here, these 8, among these all 8, they are all diastereomers of each other. Okay. So dear students, you are given this compound and you have been told to convert the given Sauer's projection. See, this is a Sauer's projection, you remember, right? Sauer's, Newman into Fisher. So into Fisher projection formula you have to convert. Okay. What you have to do here is, you remember I have told in Newman projection that eclipsed form can only be converted into Fisher projection. Here also the same rule is applicable. Okay. The rule is eclipsed form can be converted. Now first of all look at this. Yes, it is Y-shaped. Okay. So I am telling you the simple logic to convert. First of all, if it is not in Y-shaped, make it by rotating 60 degree or something like that. If it is staggered, first of all, by just rotating from any side 60 degree, you can make it eclipsed. How? Y-shaped. Simply first of all make it Y-shaped. Okay. Now observe this one. What you find? this is a chiral center HDCH3, this is also chiral center HDCH3. Okay, so first of all, draw this part, two chiral centers, this is methyl, this is methyl. Now suppose if I say here is the observer, observer's eye. Okay, observer's eye. So for observer's eye, what you will look? For observer, this part is towards the observer, this part, see H and D part, okay, and that is also, this will be on right side, just observe it like this, okay. So this part, D part, okay, observer is watching from here, so what he will think? These two are towards him, towards the observer, okay, and these are away from him, clear? So this part will be kept at dash position in the vertical line, and these two are towards the observer. Now also, for easy purpose also, take this right side part on the right side. So here D, this D here, now H will be here, this side also H will be on left side. Means when observer will see, what he will find? He will find that, look at it like a bridge, okay, this H and D, here also H and D, okay, this methyl and this methyl. Then, so this side is D, this side is D, and these two, so this is your front, top part, CS3, and this part is your at the bottom part, okay. So for observer watching from this side, this is your front part, D right side, H left side, this part is above and this part is below. Clear to you all? So this is one of the simplest method I have told you to draw Sawhorse into Fisher projection formula. Done. Let me give you a question, simple question. Draw it by yourself. Draw its Fisher form and check whether it is meso or not. Okay. Done. Observer from this side, what he will find? Place these on right sides. Now this part on the top, COH, H, OH. Now this one, OH this side, OH, H, COH. You can see that this compound is not meso, it is optically active compound. Okay. Now let me rotate it to simply 180 degree. 180 degree to any of the side. What I find, I'm just telling you, 180 degree, because I have to make its staggered form. Okay. So just rotate this one to take this part. Means I have to make this, this and this. Okay. So when this will reach here, okay, so when this COH reach this part, okay, done, then what will happen? When you rotate this Y-shaped reverse from this side, then this will rotate to here, this comes this side, this part comes 180 degrees this side, so this part will come here and this part will come here. Okay, done. Now from this also you can observe that this is not a meso part. How? Anti parts are, this must relate with this. So here this is OH, this is not OH, this is H. So you can see this OH and this H are on same side. Okay, done. So in that way you can observe. Clear to you all? Okay. Define symmetric, asymmetric and dissymmetric molecules. Dear students, it is one of the famous question which is asked in the given compounds, whether the compound is symmetric, dissymmetric or asymmetric. Now you have to understand these three terms. Okay. Symmetric molecule means molecule is symmetrical, achiral optically inactive. Clear to you? If the molecule is symmetrical, okay, symmetrical means achiral, done, symmetric molecule. Next term is dissymmetric. Dissymmetric molecule is simply a molecule which is chiral, means unsymmetrical, which do not have POS or COS or AAOS. Unsymmetrical molecule chiral molecule which have no POS, no COS, no AAOS. See, that compound is not having plane of symmetry, it is also not having center of symmetry, it is also not having alternate axis of symmetry. You remember these three symmetry means if a compound is having any of this symmetry, then the compound will be symmetrical. Remember, so dissymmetric simply means it is not having all these three. Okay. Asymmetric molecule. Now, asymmetric molecule simply means a dissymmetric molecule which is not even having AOS. It is also not having axis of symmetry. Now, how it is possible? As we know that maximum cases we can at least generate axis of symmetry, right? So, how it possible? It is possible because a dissymmetric molecule which is unsymmetrical at all, but this molecule is also having at least one chiral center, then it is called as asymmetric molecule. Okay, so I can say unsymmetrical molecule which have at least one chiral center means it is unsymmetrical. It simply means no POS, no COS, no AAOS, but at the same time it is also having chiral center. Okay, it is not necessary that due to that chiral center it is optically inactive or active, right? But the compound is unsymmetrical. That unsymmetry may be due to biphenyl, due to cumulines or all these cases, but at the same time it is having chiral center also or chiral carbon. Okay, means I can simply say no POS, no COS, no AAOS, no AOS. Okay, remember all these four are absent. In such a case, you say that the compound is asymmetric molecule. Now the question arises, asymmetric must be dissymmetric. Remember, asymmetric will also be dissymmetric. Why? Because asymmetric means unsymmetrical, POS, AOS and COS all three absent, means dissymmetric. Okay, but all dissymmetric cannot be asymmetric. Okay, so this was one of the good question arises sometimes. Dear students, now let me tell you one more point, atrop isomerism. Now what is this? Atrop isomerism is simply one type of isomerism where compound becomes optically active. Compound becomes optically active due to steric hindrance. Means there must be huge strain in the compound. It may be due to steric crowding, it may be due to steric hindrance such that there is possibility of sigma bond, but it cannot rotate into another form. Okay, so first of all let me define. Type of isomerism where compound is optically active due to steric crowding, in simple terms. Okay, high strain on interconversion between two forms. Okay, although there may be possibility of sigma bond, but you cannot rotate it because it is having huge strain. Okay, rotational barrier is high. So that is your atrophy isomerism. Now let me give you a few examples so that you can understand simply. I can also say in simple terms that a compound is optically active. Why? Because there is steric crowding such that SIR effect occurs. Sometimes in some examples you will observe SIR effect. You remember GOC, steric inhibition of protonation. SIR means ortho effect. Okay, so if you are having bulky groups on ortho position, means 1,2 position in a benzene ring, then there is a possibility of such cases. Okay, let me tell you a few examples. Dear students, look out at this example. Here, check yourself whether it is optically active or inactive and what is the reason. You will find that in this question, particular question, nitrogen is having resonance, lone pair single double conjugation, so it is actually not chiral center. Okay, it is also in conjugation with this ring, better conjugation with oxygen as such, lone pair single double this side. Okay, because oxygen will be minus charge, that is more better case. Now this is your cis form ClCl on same side. Now this is a bulky group. Two bulky groups at ortho position, huge steric crowding. So what will happen with respect to this group? This group will be a bit rotated. Okay, now what will happen through that? As such, this carbon is in conjugation with this. Okay, double single double, so it is planar part and this part is in conjugation planar part, but due to SIR effect here, this compound is optically active. Okay, so this is one of the good example to understand that this compound is optically active. One more case. Okay, so dear students, look out at this example. In this example, see, this is arsenic. You remember nitrogen family, NPAS-SBBI, NPAS. So it can form 4 bonds. These 3 are same and this part is also one different part. As you know, this is sp3 hybridized. So taking this methyl and this part, and if you cut, then you can get symmetrical part because these 2 are methyl same. Okay, but here also due to steric hindrance. Why? Because this is also one of the bulkier group. Okay, so due to this, here also you are having trouble in cutting into 2 equal halves. Okay, clear to you? Okay, so I think you have understood this part. This will be your optically active. Although it is not a chiral center here, these 3 are same, only one different. But why? Because if you cut taking this part and this entire part, then what happens? Here you are having bromine as well. So this steric hindrance part will not let it to cut in equal halves. Okay, because it is not as such planar part. You remember? Clear? Suppose if this bromine is replaced by hydrogen, then definitely it will be optically inactive. Okay, here it is optically active. Such cases can be explained in best way using biphenyls or triphenyls. Let me give you CH3 Br 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 OH OH. It is methyl 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 methyl. Don't be tensed with this example, okay? Very simple example I am just taking, don't worry. So in this example you have to observe whether this compound is optically active or this compound is optically inactive, okay? So students, just observe. You remember this methyl methyl and this bromine and OH, it is having steric hindrance. So if I say this ring and this ring, so if it is in plane, then this is in perpendicular. So with this, with respect to this is in plane, assume this is in the plane of this board. So this is perpendicular. See, this is like this, then this part is like this, okay? Then this part with respect to this, it is perpendicular. So this will be again in the plane. In plane means just like if you are having two rings perpendicular to each other, three, then first and last are in the same plane, okay? So let me check it is having POS or COS or not. If I take this as center, then this OH, this OH, this Br, this Br. But from this side methyl, that is okay. This side bromine, but this side is not bromine. So I can say COS is absent. Clear? COS is not present here. Now, POS. See, this is perpendicular. So if I cut in this way, then this part and this part is exactly same. Here you are having bromine, here you are having bromine. But unfortunately, this is bromine here and this bromine is this side. So if you cut like this, no POS. Okay. So dear students, this is not having POS, not having COS. It is an optically active compound. Clear to you? So it is triphenyl part, 3 benzene rings connected to each other. Okay. Draw all possible isomeric ketone having molecular weight 100. Okay. So dear students, in this question you are asked to draw the ketones having molecular weight 100. Now there are many questions arises in mind. First of all, which compound you have to choose? See, you have been told ketone. Be specific. It is not diketone because you have been told only ketone. Don't take isotopes of hydrogen. Always use hydrocarbon having ketone part. Simple. Okay. And you have to draw the isomers. Now when you say all isomers, then it must include stereoisomers as well. Okay. Now you have been told molecular weight 100. So here you need to understand that one oxygen will be there, C double bond O part, this R part and this R part, such that molecular weight is 100. Okay. Now let us suppose C5, hydrogen we will consider anything. Okay. Then O. So for 5 carbon atoms, it is 12 5s are 60 plus oxygen 16. So it will be 76. No, that much hydrogen will not be there. Let us suppose C6. Oh, then it will be 12 6 are 72 plus 16, 88 plus 12. Yes, it is possible. So there is a possibility of C6H12O. See, in this way, first of all, you have to understand that which is the possible compound. Now our compound is fixed, C6H12O. Okay. Now let me check it. Just draw a random structure, first structure. 1, 2, 3, 4, 5, 6. For ketone, this is the case. Okay. So it is 1, 2, 3, 4, 5, 6. Now check it. Hydrogens. 3 plus 2, 5, to 7 to 9 and 3, 12. It is C6H12O. Okay, so molecular weight 100, this is the possible compound. Done. Now let us draw all possible isomeric ketones. First, take the case of 6 carbon chain. In 6 carbon chain, you have two possibilities. 1, 2, 3, 4, 5, 6. Second carbon is having C double bond, or third carbon is having C double bond. Two possibilities. Now, let's take the case of 5 carbon atoms chain. 5 carbon atom chain. Then C double bond is here at C2. Now you are having two possibilities. One is having methyl at 3 position or having methyl at 4 position. Okay, both possibilities are there. Now in the same case, if you are having 5 carbon chain, then also you are having possibility of making C double bond at 3 position. Now you are having one possibility. Okay. Now one more case is there. If you take 4 carbon atoms chain, suppose see, this carbon is having CMe3 and this is C double bond O CH3. Okay, 1, 2, 3, 4, 5 and 6. It is 6 carbon chain. So these are the all possible cases which I have drawn. Now you cannot think any other case. If it is possible, just think by yourself. First case, consider the case of 6 carbon chain, 2 cases, 5 carbon chain, 3 cases, because C double bond at C2 or C3. At C2 then 3 methyl or 4 methyl. At C3 then 2 methyl. From this side or this side, same thing. Now 4 carbon chain. So the only possible case is, obviously you have to make C double bond or ketone part, not in corner. So 2 methyls. Okay, this is the only possible case. 3 carbon chain, not possible. Now among these, now you have to consider ketones are there. Now isomers, total. So it is not optically active. No chiral center. Yes. See, this one is a chiral center. How? This is having CH3, hydrogen, ethyl this side and COCH3 this side. So this is a chiral center. No chiral center, no chiral center, no chiral center. So for this, 1, 1. For this one you have 2, for this 1, 1 and 1. Total will be 1, 2, 3, 4, 5, 6 and 7. So answer will be, total possible cases are 7. Clear to you all? Okay. See, find total stereoisomers of camphor. Now first of all the question arises, what is camphor? Camphor is actually an organic compound. Okay, camphor is an organic compound. Now let me draw its structure first of all. Okay, so dear students, this is the compound camphor. Okay, now you can check, it is actually 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. C10, H, 1 oxygen, hydrogen 3, 3, 6, 7, 8, 9, 10, 11, 12, 13. Okay, so you are having 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 carbon atoms, then 1 oxygen, then hydrogens are 3, 3, 6, 1, 7, 8, 9, 10, 11, 12, 13. So H13O, this is your camphor, solid compound. Okay. Now in this compound, if I have to check the number of stereoisomers, first of all check the parts which are showing stereoisomerism. So I can observe this is a chiral center because CH3 this side, C double bond O this side, this is CH2, but this is a 3 degree. Imagine this structure in 3D. Let me draw a possible structure of this in simple, just to make you observe what this compound shows. See, this is your now you can understand easily. This is your 6-member ring part. Okay. Now from bridgehead, you are having structure like this. Now from this part is a CH3. This is your C double bond O. Now 1, 2. From this position you are having 2 methyl here. Okay. This methyl from this carbon and this methyl. Now check it. Correct? Okay. Now here you can check 6, 7, 8, 9, 10. 10 carbon, 1 oxygen. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. It is done. Okay. It is C10 at 16. Okay. This is the correct formula. Now in this, if you check, this is a chiral center and this is also a chiral center. 2 chiral centers we are having. Now if I put the formula, what I will get? 2 to the power 2 gives 4. But this is incorrect. Okay. Why incorrect? I directly told incorrect because see, it is a restricted rotation compound. Why? Because it is a bridgehead part, it is also a bridgehead part. Suppose this is having configuration R, suppose, and this is also having configuration R. Okay. If you interchange these two groups, this part and this part, if you just interchange, because by one interchange you will get its enantiomeric part. So you can observe on interchanging this part, definitely this part will also be disturbed because it is a ring having restricted rotation. So if it is R, it is R. You cannot make this S part and this R. If it is RR, then the other part will be SS. Okay. If it is RS, other part will be SR. Only 2 enantiomeric pairs are possible here. Okay. So I can tell that here total number of possible cases will be total stereo isomers in camphor equals to 2 from this part and this part. 2 chiral centers. Okay. Actually you can say it as rigid chiral center. Means disturbing one chiral center will automatically disturb the other chiral center. Okay. See, the question is it possible that any compound is not having POS or COS but having alternate axis of symmetry? Means the compound should not be having plane of symmetry, no COS, but it is having alternating axis of symmetry. So students, yes, it is possible. I'll just show you a compound which is having no POS, no COS, but it is having alternating axis of symmetry. Okay. Okay, just look at this compound, a very famous popular compound. In this compound, if you see that this nitrogen is sp3 plus charge, so if this ring is towards the in the plane itself, this part and this part, then definitely this is perpendicular. This is perpendicular and this is planar. Okay. check the configuration of the given compounds on hydrogenation, and you are given two compounds, okay. This is the first compound, and second compound is this compound, okay. Now here you have to check the configuration, means RS configuration, right, in these compounds. So first of all, let us draw on hydrogenation what this compound will give. Hydrogenation means addition of hydrogen, okay, simply addition reaction. So what this compound, see here this compound is a chiral carbon. Why? Hydrogen this side, bromine this side is ethyl, and this side ethynyl. On hydrogenation it will become now this carbon is having ethyl this side and this side also ethyl. So there is no use of saying this carbon is a chiral, okay. So no chirality, so no configuration, okay. Now you can say for this compound optically inactive. Clear to you? So you cannot say RS configuration here. Now check this compound. If you check this compound on hydrogenation, what will happen? On hydrogenation, this compound will give you have to make this part as it is only, okay. Now this part was double bonded, now it will become single bonded. How? You have given H2 here, hydrogenation, addition of hydrogen in this alkene becomes alkane, okay. Now you have to check RS configuration in this part. Simply if I have to check, this bromine will be 1, this part is 2, and this ethyl is 3, hydrogen is 4. So from 1, 2, 3, it is anti-clockwise, so the configuration will be S configuration. Clear to you? Find total number of cyclic ethers for the molecular formula C4H8O including stereoisomers, okay. Now first of all do it by yourself. For given compound C4H8O, you have to find out cyclic ethers possible, okay. So if I check this compound, it is having degree of unsaturation du or dBe equals to 1, means either one pi bond or one ring. Simply you have been told cyclic ether, so you have to consider the cases of ring, okay. So I am just trying to draw all the possible cases. One case is 5-membered ring. If you remember the name of this compound, it is tetrahydrofuran, okay. Now let's check 4-membered ring. In case of 4-membered ring, you can make one methyl, then this part CH3, or one more possibility, this CH3. Let me check the formula. 1, 2, 3, 4 carbon, 1 oxygen, 2, 4, 6, 8, okay. Possible, same. This one also. Now let me draw 3-membered rings. 3-membered ring. Now one possibility is you can make both methyl on same position. One more possibility is make one methyl on both positions, and one more possibility is make ethyl, okay. 3-membered ring. So these are the possible structures I have drawn. See, structures I have drawn. Now let's check if they possess any stereoisomerism, okay. If there is geometrical isomerism or there is optical isomerism. This will be having only one structure, no stereo. See, as you are having this 4-membered, considering as rigid, this oxygen and this methyl, this carbon and this methyl, you can cut it, okay. So it is having only one structure. Clear? Because this is not a chiral center. From this side oxygen, this side same. Now considering this part, you are having one chiral center, CH3H, oxygen and carbon. So for this you will get two possible cases. Its enantiomer will be there. Means one time methyl on wedge and once in dash. Okay. Now check this one. No chiral center, so only one possible case. Here in this one, this is a chiral center and this is also a chiral center. Now you remember this case when two chiral centers, but numbering can be done from both sides. Total will be 3. If you remember, n is even. Okay. 1 meso and 2 active. Now let me draw it. How? When both on wedge, then it will be meso. Means optically inactive. You will be having plane of symmetry. Okay. When one in wedge and one in dash, it will be optically active. So its mirror image will be taken. So 2 active means I am telling enantiomeric pair and 1 meso, total 3 for this one. Now check this one. This is having one chiral center, so it is having also 2. Now if I check the total, 1, 2, 4, 5, 3, 8 and to 10. So the answer will be 10. Clear to you all? Total cyclic ethers for C4H8O will be 10. Okay. Find total number of stable conformers for the given compound having non-zero dipole moment. And the given structure is now this is your structure given. Okay. So for this you have to draw the conformers. Now dear students, here we need to draw the Newman projection formula for this Fisher projection formula, the reverse case which we studied in last lectures. Okay. So let's draw first of all. See, as we know, for the Fisher, I can draw its eclipsed form first of all. This as front. So you are having bromine here, methyl here and chlorine here. Okay. Now from this one, so this methyl and this chlorine this side only and this bromine this side only. Okay. So for this I have made this conversion. Clear? Now total number of stable conformers, as we know, among eclipsed and staggered, eclipsed is unstable. Don't consider it. Now first conversion is there. Now just rotate it by 60 degree. 60 degree rotation. What you will get? Keeping front as it is, rotating the back part, you will get Cl, Me and Br as it is clockwise 60 degree. Okay. So methyl comes here, this chlorine comes here and this bromine comes here. Clear to you? Okay. Now this is a stable, but it is having dipole non-zero, mu non-zero. Okay. Now understand, if I rotate this part again 60 degree, I will get its eclipsed form, which will be again unstable. I need not to consider. But another case can be, if I rotate it 120 degree, what will happen? 120 degree. 120 degree clockwise from back side. Because on rotating 60 degree, I will get eclipsed form, that is unstable. And I have to draw the stable conformers. So 120 degree backside. Chlorine, bromine, methyl. Now this methyl 120, 60 here, 60 here. This methyl comes here. Okay. Then this chlorine comes this side and then bromine comes this side. On rotating it 120 degree. Clear to you? Okay. Now again let's do one thing. Rotate 120 degree clockwise. Why? Because you can observe for this one, on 60 degree rotation, what you will get? By 60 degree rotation, it will become again eclipsed form. Okay, on rotating backside 60 degree, you will get eclipsed, which is not possible because it is unstable. And you have been asked stable conformer. So 120 degree from backside clockwise. Cl, Br, Me, chlorine comes this side, bromine comes here, and methyl comes here. Okay, so dear students, these are the possible staggered conformers for this particular given compound. Okay, because you have been told for this part you have to make non-zero dipole moment compound. Okay, so you can check, this is having non-zero dipole, this is Br same opposite, but here Cl and Me, Cl Me, so it is again having mu non-zero. Check this one, Me front, but Cl Br, so it is also having dipole moment non-zero. Now what happens if you rotate it 60 degree further, you will get this same compound again. Okay, so whatever possibility was there, I have drawn all the cases. So the answer will be 3 possible cases. Total stable conformers which are having non-zero dipole moment for the given compound is 3. Okay, so students, I have drawn a few questions. Here you have to find out whether the compound is optically active or inactive. Okay, do it by yourself first of all. Okay, done. Let me check. See, in this compound, if I see, nitrogen is having lone pair, single, double, conjugation, here also conjugation, 6-membered ring, consider the ring as rigid structure. If I take this plane which cuts this methyl and this part, then it is having plane of symmetry, but center of symmetry is absent, okay, because from this CO, this NH. Now second, if I see, if I cut in the same plane like this, then this part and this part is okay, but this CO is here and this CO is here, no POS. But yes, from center, this CO, NH, this side up methyl and this down methyl. So here COS is present, POS is absent. Okay, now check this question. In this question, this is having pH upside, COH upside. See, it is very easy here because either you consider a plane having COH and COH. So pH will be in front of each other, mirror image relation. So it is having POS present, but COS absent. Check this one. Again, I have made one interchange only. pH up, pH down, COH up. Simply here you can say from this center up, down, up. So it is having COS present and POS absent. Okay, now check this one. See, if you remember, 1 benzene, 1 ring, benzene, 2 is naphthalene, 3 is anthracene. So it is having plane of symmetry, POS present. It is also optically, these both are optically inactive because both are planar. Okay, so in all these questions I can say POS, COS, one of the symmetry is present, so all are optically inactive compounds. Okay, so students, in these compounds you have to check whether the compounds are optically active or inactive. Okay, check whether it is having POS, COS or not. So first case, see, earlier I told you about naphthalene and anthracene. Now this is your phenanthrene. You remember phenanthrene. If the benzene comes this side, then it is anthracene, but it comes this side, phenanthrene. So it is having planar structure, so POS present, planar. Now this, when 4-membered ring, in 4-membered ring also, see, remember, this one, this connectivity same, POS present. Here also, this ring, connectivity same, then same, then same. Similarly, here 3, here 4, okay. Here also, plane of symmetry present. If I have to consider the further cases, I am just telling you a hint. If you make 5-membered, same 5-membered case, that will be optically inactive, POS will be there, okay. But if you draw 6-membered similar case, then it will become optically active because no POS, no COS in 6-membered ring, remember, okay. Clear? Now check this case. If you remember, it is cumulene. 1 pi bond planar, 2 pi bond perpendicular, 3 planar, 4 again perpendicular. As this is perpendicular to each other, now it will be surely bromine iodine 2 different, fluorine chlorine different. So it is optically active. Its mirror image will also be there. Active, no POS, no COS. See this one. Now here you need to imagine just like cumulene. It is having lone pair and H. It is also having lone pair and H. Okay. don't consider it as a planar part as it is, okay, because this nitrogen and H, these are perpendicular to each other, and two groups, lone pair H, so it is also optically active. Check this one, this double bond and 4-member ring as earlier told, okay, this can be considered again pi bond type, so 2 pi bond perpendicular, HCS3, so it will be optically active, no POS, no COS. Now check this one, see both are same, what difference has been created? Chlorine, HCS3, same groups, so if you cut such that hydrogen and methyl is cut in 2 equal halves, then this chlorine and chlorine will be on 2 different sides. See, if the chlorine is like this, 2 sides, then this H and CS3 will be up and down. So you cut like this, chlorine 2 equal halves, okay, HCS3 2 equal halves like this. So it is having no activity, plane of symmetry present. Okay, clear to all? Okay, so students, with these illustrations, I feel that you have understood about entire optical isomerism as well as conformational isomerism.